So this is actually one of my favorite topics of the semester because it's really cool, and it's algebra that's simpler than what we do with numbers, which is kind of exciting because that doesn't always happen. So what we're going to be talking about is partial fraction decomposition, and what we mean is essentially we're going backwards. Okay, so let's say, for instance, we'll look at this with numbers first, just so that you know what we mean. Let's say, for instance, that we have the fraction 4/6. What we're doing is we're figuring out, well, what are two fractions or two rational expressions that we can use that will add to 4/6. Now, the problem with numbers is that there's so many of them, right? So, for example, 4/6 could be 2/6 plus 2/6. It could be 1/6 plus 1/2. It could even be negative 1/6 plus 5/6. We could say it's 1/3 plus 2/6, okay, which we know is the same thing as 2/6 plus 2/6. Okay, but there are a tremendous number of ways that we can divide up this 4/6. You might have done this even if you remember way back in elementary school, where they say, well, okay, how can we get to 10? Well, we can get to 10 by doing 8 plus 2. We could get to 10 by doing 1 plus 9. We could get to 10 by doing 3 plus 7, or 4 plus 6. There are lots and lots of different ways. Algebraically, there is only one way. So if we have a rational expression, there is only one set of fractions that we can use in order to get to that fraction, and we call this partial fraction decomposition. Okay, so let's write down what we're doing essentially. So we're writing a rational expression as the sum of simpler rational expressions. So here, there are many possibilities, right? Many different ways to do this. Algebra, or we would say in rational expressions, and the reason why we say in rational expressions is an expression is an indication of algebra here, okay? So I'll put in parentheses algebra. We're not just talking about numbers, we're talking about an expression like x plus 6. Or x squared minus 2x plus 1. That's what we're talking about here. Okay, so in rational expressions, there's only one way, which is why we can do this easily here. But in numbers, it can be much harder. So you can see here, well, yes, we can do this, and we might be able to do it relatively easily for something like 4/6, but if we had something like 23/210, then it's going to be a lot harder to come up with lots of different ways to come up with all of the different fractions. Plus, there are a lot of different ways to do it, right? So 10, the number 10, if we come up with all of the different numbers that we can add together to give us 10, it can become a lot. And sometimes it's more than two numbers, right? We could do 1 plus 5 plus 4. So with partial fractions, which is what we're working with now, there's only one way regardless of the number of fractions that you use, okay? So I'm going to just essentially go through an example with you, and I will just do a bunch of these. They kind of work in different ways, and we won't go through every possibility. For some of them, I might just say, okay, well, here's how you get your denominators, or here's the process that you would follow, because some of them are more complex, okay? So we're going to start with proper fractions. So when we say a proper fraction, with numbers, what we're saying is that the numerator is less than the denominator. Four over 6 is a proper fraction. 2 over 7 is a proper fraction. But if you have something like 7 over 3, that would be improper. In that case, the numerator is greater than the denominator. Okay. If the numerator equals the denominator, then it's irrelevant because our fraction is just 1. When we talk about rational expressions, what we're saying is that the degree of the numerator, because when we have x's, we don't really know except by looking at the degree. So here we're saying the degree of the numerator is less than the degree of the denominator. So we're going to look at those first, and then improper fractions is going to be more like my telling you what the process is, but we're not actually going to do it necessarily, okay? So the first thing that we're going to do is we're going to factor the denominator. So we're going to do an example, and then as we do this, we'll give you the steps, okay? So our first step, let's actually create the problem first, and then we'll look at the steps. So we have x plus 7 over x squared minus x minus 6. And we want to know what fractions can we add to get to this, okay? So our first step is to factor the denominator. Do this in a different color. And you want all of your factors to be either linear or quadratic. Now these words, as much as possible, are critical. And the reason why they're critical is that you can see here that this denominator is quadratic, but it's not factored as much as possible. Okay, this we can factor further. So when we say as much as possible into linear and quadratic factors, we know that there are some quadratics that are not factorable. And for those quadratics, you would leave. But this quadratic is factorable. Okay, so let's do that. So again, we're not going to go through the factoring process. I'm going to assume that at this point you know your factors. Okay, so this factors to x minus 3 and x plus 2. Okay, so what you're going to do is you're going to create fractions. Each one is going to have one of the factors as the denominator, okay? And you'll see what we mean by this in a second. So you're going to create a fraction for each factor where the denominator is the factor and the numerator is a constant. We'll call that constant, for example, A, if the factor is linear. And we'll do examples with both cases. If the factor is quadratic, then we would write it as ax plus b. So here's what we're saying. We're saying that we have x plus 7 over x minus 3 times x plus 2. And we're going to separate this into different fractions. So the first fraction is going to have a denominator of x minus 3, and the second fraction is going to have a denominator of x plus 2. Okay. And in the first fraction, our denominator is linear here. X minus 3 is linear. So the numerator is just a constant. We'll call the first constant A. And over here, this is also a linear denominator. So we'll call our second constant B. Okay, so it's a constant. We use the letters of the alphabet to help us. And we'll do some examples where we're going to have quadratic factors, just not yet. Now what we're going to do is we're going to multiply both sides by the denominator on the left, by the original denominator, okay? The denominator of the original fraction. And think about what that means. What that means is that we're going to get rid of all of our denominators. So over here, we're going to multiply by x minus 3, x plus 2. And over here, we're going to also multiply by x minus 3, x plus 2. It cancels. So on this side, it cancels. And what we're left with is an x plus 7. Now here, when we multiply this by, remember this gets distributed, right? So you're multiplying a over x minus 3 by this, and you're multiplying b over x plus 2 times this. Okay. Now when we multiply a over x minus 3 times this, the x minus 3 will cancel. Okay, so you're getting rid of your fraction here, and the only thing that you're left with is a times x plus 2. And then something similar happens with the b. The x plus 2 cancels, and then what we're left with is x minus 3. Okay, so our next step is to actually solve for x. Figure out what x is equal to, okay? So it's actually, that's not true. We're not solving for x, we're solving for a and we're solving for b, okay? So I'm gonna put over here that we're solving for the constants. And there are actually two ways that we can do this. One way is significantly easier than the other, but it doesn't always work. So it's kind of like a lot of the other things that we've done. For example, when we solved exponential equations, right? We said if we had something like 2 to the 3x plus 1 equals 8 to the 4x minus 7, we said that you can express both sides with the same base, and that's the easier way to do it, but it doesn't always work because you can't always express both sides with the same base, okay? Our other method was taking the log of both sides. The same thing is true for factoring, right? We said, okay, well, factoring is easier, but it doesn't always work. Quadratic formula or completing the square always works. So we've come up against this before, that sometimes there are easier methods or really shorter methods versus longer methods. I'm going to show you the method first that's shorter, okay? That's faster. So let's rewrite this on the next page. We have x plus 7 is equal to a times x plus 2 plus b times x minus 3. And in this case, we had two linear denominators. So when we do this, both methods, neither method is going to be particularly difficult. When we wind up with quadratic factors, then both methods are going to be longer. There's not really a better method, and sometimes it might be easiest to use both. So I just want to warn you ahead of time that that's coming, okay? So the first method is to plug in values of x that will make all but one of the constants disappear. It's really important that it's only one of the constants that stays. And when we say constants, we're talking about the a and the b. So in this case, we only have two constants, so we're only trying to make one of them disappear. So we're saying, okay, well, what's a value for x that we could plug in here that's going to make this a go away? And a value would be -2, and the reason for that is -2 plus 2 is 0, and 0 times anything is 0. Okay, so if we plug in an x equals -2, this goes away, and then we can solve for b. Then you're just going to repeat the process in order to find a. If you're lucky, you'll be able to do this for all constants. So we're going to start with x equals -2. Because as we said, if we plug in x equals -2, this becomes 0. So we have -2 plus 7 is equal to a times -2 plus 2. So I'm putting in all of the different steps so that you can see what's actually happening. Plus b times -2 minus 3. Okay. We get -5. Sorry, we get +5 here. Then we get a times 0 plus b times -5. Okay. And again, I'm putting in all of these. So -5 is equal to 0. Minus 5b. So I just brought the -5 out front over here, right? B times -5, or -5 times b. Okay, plus -5b is the same thing as minus 5b. So that means that -5 is equal to -5b. I'm sorry, I keep writing -5. 5. Divide both sides by -5. And what you get is b is equal to 1. So we solve for b. Now we're going to repeat this process. We're going to plug in a value for x that's going to help us get rid of the b. So if we look at the b, a value for x that we could plug in is a 3, because 3 minus 3 is 0. So now we're going to do the same thing, but we're going to plug in x equals 3. So now we have 3 plus 7 is equal to a times 3 plus 2 plus b times 3 minus 3. And again, we're going to put in every step here. So 10 is equal to a times 5 plus b times 0. So we can say 10 is equal to 5a. And then plus 0. B times 0 is 0. So 10 is equal to 5a. Divide both sides by 5. And we get that a is equal to 2. So now we have both of our constants. Now we're almost done. Now we just need to plug in. Okay? So our original problem was x plus 7 over x squared minus x minus 6. And if we go back to the previous page, we can see that we said that that was a over x minus 3 plus b over x plus 2. Well, now we know what a is. A is 2 and b is 1. So we're just going to plug that in. So it's going to be 2 over x minus 3 plus 1 over x plus 2. Notice we're plugging it into the original. We're not plugging it into here. Okay? And if we did plug it in here, you would see if we plugged in a and b, so 2 times x plus 2 plus 1 times x minus 3 will give us x plus 7. So you can always check, and b here is -1. Sorry. B is -1. So in the bottom, we can do one of two things. We can either write this as 2 over x minus 3 plus -1 over x plus 2, or you can just write it as 2 over x minus 3. Either way is fine. you can move the negative in front. So either one of these. I'll box the whole thing so that you know that any of them are fine. Okay. So this is the first method. So again, let's just review. We looked at what we had once we multiplied by the denominator that was on the left, and we said, what values can we plug in for x that's going to make every constant disappear except for one of them? Because remember, if we have only one unknown, we can solve for it in an equation. So we looked at what we were multiplying a by, and we said, how can we make it 0? So in order to make x plus 2 0, we just plug in x equals negative 2. We plugged in x equals negative 2, and then we were able to solve for b. Now we made the b disappear. We said, okay, well, what could we plug in for x that would make x minus 3 equal to 0? Because b times 0 is 0. So we plugged in x equals 3, because 3 minus 3 is 0. And then we were able to solve for a. Once we solved, all we did is we went back to the original fraction and we just plugged in, okay? So we had 2 over x minus 3, because originally it was a over x minus 3, plus negative 1 over x plus 2, because originally it was b over x plus 2. And the negative could go just in the numerator here, or you could just put it in front of the fraction and turn this addition into subtraction. There is only one way, only one set of fractions that we can add or subtract to give us x plus 7 over x squared minus x minus 6. These are the two fractions. That's it. Okay, there's no other way to do it. Okay, this is one way to solve for the constants. There's another way to solve for the constants. So let's look at that other method, and sometimes we'll use one method, sometimes we'll use the other. On rare occasions, we'll do it with both just so that you get accustomed. Okay, and you'll see that in some cases, this second method, even though it always works, it can be a lot more complicated. So you may be combining the two methods where you might be able to cancel out everything but the a, but you can't cancel out everything but the b, okay? So again, all of that will make more sense as we do more examples. So let's do the second method. So what the second method does is it says, okay, distribute and then rearrange your terms in standard form. So we're going to say rearrange your terms so like terms are together. And the exponents of x decrease. That's what we mean by standard form. What we're going to do is we're going to set the coefficients equal to each other. And this is not going to be clear until we actually do it. So we're going to set coefficients on the left equal to corresponding coefficients on the right. And that's not going to be clear yet. Again, I'm going to rewrite this. We're going to do this on the other page, on the next page. So I'm going to rewrite it. We have x plus 7 equals a times x plus 2 plus b times x minus 3. So notice that very first step of getting rid of the denominators. is the same. Okay. So all we're going to do is we're going to start off by distributing. So this A is going to get distributed, and this B is going to get distributed. So what that gives us is x plus 7 is equal to ax plus 2a plus bx minus 3b. Okay. Now we're going to rearrange these terms on the right. So when we rearrange the terms on the right, we're going to group them by the powers of x that it's being multiplied by, so by like terms. So ax and bx would be considered like terms because they have an x to the first. 2a and negative 3b would be considered like terms because they have no x, which means that they have an x to the 0. So we're going to rearrange, and we get x plus 7 equals ax plus bx plus 2a minus 3b. And this is going to be a little bit like the beginning of factor by grouping. We're going to look at each of these individually. Okay. And all we're going to do is we're going to factor out the x here. So here there's nothing to factor out, right? But here we can factor out an x. So it's going to look like this. It's going to be x plus 7 is equal to, we're going to put the x actually behind. And then I'm going to put this in parentheses. We're just going to put all of our constants in parentheses. So now we have a plus bx plus 2a minus 3b. So we put it in parentheses because we can. There's nothing that would prevent us from doing that. This is a plus sign, so we don't have to distribute anything. Here, we pulled the x out and we moved it to the back instead of to the front. It doesn't matter. It's just that this is actually going to make it easier to see what we do next. Okay? If we redistributed this x back into the parentheses, we would get ax plus bx. Okay? So we distributed, we rearranged so that it's in like terms, and we put it in order, so the x to the first, then the x to the 0. And then we factored out the x's. Okay? Well, now we have like coefficients, we have like terms, because we have an x here, and the coefficient of x on the left is equal to 1. Now that has to equal the coefficient of x on the right. So a plus b is equal to 1. And then 2a minus 3b is the constant that's on the right, and that has to equal the constant on the left. Okay? So the coefficient on the right coefficient of x on both sides has to be equal. And this is true for x to the first. It's also equal for x to the 0. So the constant is on both sides. And we've certainly done this before where we've said the bases are equal, so the arguments are equal, or the bases are equal, so the exponents are equal, or we just did it recently with the rational expressions where we said the denominators are equal, so the numerators are equal. This is the same idea. The coefficients have to be equal. So a plus b is equal to 1 because the coefficient of x is 1. 2a minus 3b is equal to 7 because they both represent constants. Okay. Now here's why this we tend not to like as much. Okay. The reason why we don't like it as much is because this isn't quite as simple to solve. Okay. What we have to do is, this is a system, so we can solve by solving the way we would solve a system. So in this case, solving the system, we would multiply the first equation by 2, or really by -2. This is one option. So we would wind up with the two equations, -2a minus 2b is equal to -2, and then 2a minus 3b is equal to 7. So we're solving it like a system. It is a system, so it's not like a system, it is a system. And we get -5b is equal to 5. Okay. So notice it works exactly the same way. We get that -5b equal to 5 again. We had that in the other one, okay, as well. We wound up with a -5b is equal to 5 here. So we divide both sides by -5. So notice we're solving. And we're solving using elimination. It is perfectly fine to solve using substitution. So we got b equals -1. And then you can either find a by doing by eliminating b, so you can multiply this by +3, or you could just plug in here. A plus -1 is equal to 1. So you can add 1 to both sides. And if we add 1 to both sides, we get a equals 2. Sorry, I meant to say +1. And then you would do the same thing that we did before. You would say, okay, so x plus 7 over x squared minus x minus 6 is equal to 2 over x minus 3 plus -1 over x plus 2. Okay, so you're just plugging in for the a and the b. So you could see that this one can sometimes be longer. It's not always longer. Let's do another example. Let's do... I'm going to put a 1 and a 2. And then we'll do some with quadratics. So let's say that we have x minus 8 over x squared plus 7x plus 12. Okay, so we're just going to go back through. And we're going to go through the same exact process all over again. Okay, so if you remember from before, our first thing was to factor the denominator. So if we factor this denominator, we get x plus 4 times x plus 3. And in this case, we can separate this. It's going to be separated into two fractions. So the number of fractions that you separate it into is going to equal the number of factors in this case. Okay, so So we're going to have two fractions. If this had been x plus 4, x plus 3, x minus 2, we would have three fractions here, okay? So that means that x minus 8 times x plus 4 times x plus 3, we have two fractions. Each one has a factor. So the first one has a factor of x plus 4. The second one has a factor of x plus 3. The order in which you write this doesn't matter, okay? You'll get the same answer at the end. So here, this is linear, so x plus 4 is linear. So we have a constant of a on top. X plus 3 is linear, so we have a constant of b on top. If you switch the factors and you make this x plus 3 and this x plus 4, your a and your b will just be switched. So if you look at your work versus the person next to you, your work is going to look very similar. It's just that the x plus 3 is going to be next to an a instead of next to a b, but ultimately your answers are exactly the same. Okay, so remember that our next step is to multiply both sides by the denominator on the right. So this is going to get multiplied by x plus 4, x plus 3. The purpose of this is to get rid of the denominator. Okay, we want this to cancel. That's the whole point. And then we do the same thing over here. And that's going to get rid of the denominators. Okay, it's exactly what we did with the linear equations where we multiply by the least common multiple. That's what we're doing here. We're multiplying by the least common multiple. Okay, so our first thing was to factor. Our next thing was to multiply by the denominator on the left. This should get rid of all of your denominators. If it doesn't, then you probably did something wrong. So what are we left with then? We're left with x minus 8 is equal to a times x plus 3, because the x plus 4 is going to cancel. And then plus b times x plus 4, because the x plus 3 cancels, right? So if we put b times x plus 4 times x plus 3 over x plus 3, the x plus 3 cancels. Okay. So let's use the first method here. So our next step is going to be to distribute. Sorry, not to distribute. Our next step is going to be to plug in values for x. That make all but one of the constants disappear. The way to do that is multiplication by 0. So I'll rewrite this on the next page and we'll continue there. We can do this using both methods again, just so that you get familiar with it. So we have x minus 8 equals a times x plus 3 plus b times x plus 4. So we have to think, okay, well, what values of x are we going to plug in? So we want to make the a disappear first. It doesn't matter what you do first, but let's just do it this way because we read left to right. So to make the a disappear, we could plug in x equals -3. Essentially what you're doing is you're saying what is going to make x plus 3 equal to 0. And we already know, we've done these things a lot before when we solve quadratics. We subtract 3 from both sides and we say, okay, x equals -3. So we're going to plug in x equals -3 here. So we get -3 minus 8 is equal to a times -3 plus 3 plus b times -3 plus 4. So -3 minus 8 is -11. I'm going to write the 0a here. And then -3 plus 4 is +1. Which means that what we get is that -11 is equal to b. We don't even have to do a lot of solving. So that's in order to eliminate the a. Now let's eliminate the b. So in order to eliminate the b, we have to plug in -4. So let's do that on this side. So now we have -4 minus 8 is equal to a times -4 plus 3 plus b times -4 plus 4. -4 minus 8 is -12. -4 plus 3 is -1, so we get -12 equals -a plus 0b. So this gives us -12 equals -a, or a equals 12. So this worked out really nice and neat. Okay. And then we could go back and we could plug this into the original fractions. So we're going to plug it in here. Okay. So we could write x minus 8 over, we had x squared plus 7x plus 12. Is equal to a, which was 12, over x plus 4 plus b, which was -11, over x plus 3. And again, if you wrote 12 over x plus 4 minus 11 over x plus 3, that's exactly the same thing. Okay? I'm not going to write it in both ways, just because I don't want you to feel that you have to write it in both ways, but it is acceptable to write minus 11 over x plus 3, and a lot of people prefer it because then they don't have these negative numerators. Okay, so let's do one more example with just linear, and we'll do it with 3 factors. Okay. And in this case, we'll look at both methods. So let's take a third case. Okay. Let's say that we have 2x plus 1 over x plus 3, x minus 1, x minus 2. So I'm already factoring the denominator for you, just because I don't want to be factoring cubics right now. Okay. And this is a proper fraction. The degree of the numerator is less than the degree of the denominator. Let's even make this 2x squared plus 1, just so that you see what happens when we have something that's squared. Okay. So in this one, we have 3 factors. So 3 factors means 3 denominators. So we're going to have a denominator with x plus 3. We're going to have a denominator with x minus 1. And we're going to have a denominator with x minus 2. Every one of these is linear. So each one gets an A, a B, and a C. So notice we just move through the alphabet. So here we could skip the first step. We didn't have to factor. It was already factored. So now we multiply everything by the denominator on the left. And I'm going to write it like this, because it doesn't really matter. X plus 3, x minus 1, x minus 2. that means that this is going to cancel. That's the whole point. Okay, so here's the difference. This is going to give us 2x squared plus 1 is equal to a. And this time, not more cancels. Sorry, not everything cancels. It's not as simple, right? We're left with an x minus 1 and an x minus 2. The x plus 3 canceled, but we still have 2 factors left. Then we have the b. Now with the b, we're left with x plus 3, and we're left with x minus 2. The x minus 1 canceled. And with the c, hopefully you could pause the tape and you could see what is canceling. You can write it out. But with c, the x minus 2 cancels. So we're going to do this using both methods, and we're going to see if this, that way you see the difference between the two methods. And in this case, the first method is still much easier, but the first method isn't always going to work. So you'll see here it works, but when we do quadratics, it's not. Okay. So here, again, we want to figure out what is an x value that we could plug in that's going to get rid of either a and b, b and c, or a and c. So let's start by trying to get rid of b and c. So remember, anything that's multiplied by 0 is 0. So if we could make either x plus 3 or x minus 2 equal to 0, then this whole thing is 0. So let's just write that. If x plus 3 equals 0, or x minus 2 equals 0, so or, doesn't have to be both, then this whole thing equals 0. Okay, and that's important because we know that there's one of two things that we could plug in that's going to make that true. We could either plug in negative 3, and then we have b times 0 times some number, which is 0. Or we could plug in 2. Now we want to eliminate b, but we also want to eliminate c. So for here we could plug in negative 3 or 2. For here we could plug in negative 3 or 1, so there's an overlap. If we plug in negative 3, we get rid of both b and c. Okay? So get rid of both b and c, and we could solve for a. Let's figure out the other numbers that we can plug in. So this allows us to solve for a. Let's see what would allow us to solve for b. So in this one, we would have to have a number that makes both a and c equal to 0. So here, if you notice, they both have x minus 1 in common. So if we plug in x equals 1, then we get a 0 here, which makes this whole term 0. And we get a 0 here, which makes this whole term 0. So what we get here is if we plug in 1, we get rid of a and c, so we can solve for b. Figure out what we can do to get rid of a and b so that we could solve for c. So again, we're looking for something that they both have in common. They both have an x minus 2 in common. So if we plug in x equals 2, then we get a 0 here, which makes this whole term 0. And we get a 0 here, which makes this whole term 0. So we're just left with this. So this is our last one. So if we plug in 2, we get rid of a and b. So we can solve for c. So let's start this. Let's do each one. So let's start with negative 3. So 2 times negative 3 squared plus 1 equals a times negative 3 minus 1, negative 3 minus 2, plus b, negative 3 plus 3, negative 3 minus 2, plus c, negative 3 plus 3, negative 3 minus 1. So this gives us 2 times negative 3 squared is 2 times 9. So that's 18. So I'll put this in as separate. Okay. 18 plus 1. Then we get a. Negative 3 minus 1 is negative 4. Negative 3 minus 2 is negative 5. And then we get plus b times 0. You don't even have to calculate this, but I'll put it in. Plus c times 0. This goes away. This goes away. So we get 19 is equal to 20a. And we could divide both sides by 20. And we get that a is equal to 19 over 20. And notice we get a fraction. I'll show you how to deal with that when you plug it back in. But it's not a big deal that we get a fraction. This doesn't make it any harder. What you'll notice is we will start doing this. We won't do the whole thing with the second method, but we'll start doing it so that you can kind of see what happens when you use that second method. It doesn't make it impossible to solve it, just makes it longer, much longer. Okay, let's plug in x equals 1. So we have 2 times 1 squared plus 1 is equal to a times 1 minus 1 times 1 minus 2 plus b 1 plus 3 1 minus 2 plus c 1 plus 3 1 minus 1. And again, I'm going to put in this extra step. You may automatically say, okay, the a and the c go away. We don't have to do that extra step. I'm doing it here just so that you see it more clearly, okay? So we get 1 squared is 1, so times 2 is 2. So we get 2 plus 1 is equal to a times 0, which should happen. You should always double check for that. Times negative 1 plus b times 4 times negative 1 plus c times 4 times 0. So 2 plus 1 is 3. This goes away, and this goes away because they're being multiplied by 0. And then 4 times negative 1 is negative 4. So we get negative 4b. And we're going to divide both sides by negative 4. So we get that b is equal to negative 3 over 4. And yes, these are a lot of work. It does take time to solve these partial fraction decompositions. It's not a short process, but it's not a difficult process either, right? All of these things, we haven't done anything that's particularly difficult. And then finally we said if we plug in 2, we'll be able to solve for c. So let's plug in x equals 2. So now we have 2 times 2 squared. So remember, order of operations, when we solve this, we do the 2 squared first. Plus 1 equals a times 2 minus 1 times 2 minus 2 plus b. You can skip some of these steps. Do not skip them all. Times 2 minus 2 plus c times 2 plus 3 times 2 minus 1. So 2 squared is 4. So 2 squared times 2 is 8. So we have a plus 1 here equals a times 1 times 0. So again, you don't have to do this step because you know you don't have to do this calculation because you already know that you're canceling out the a. But you should double check. You should always double check that you're going to wind up with the 0. And then plus b. And 2 plus 3 is 5. 2 minus 2 is 0. And then finally c. 2 plus 3 is 5. 2 minus 1 is 1. This term goes away. This term goes away. And we're left with 9 is equal to 5c. So then we divide both sides by 5. And we get that c is equal to 9 over 5. So now it's just a matter of plugging back in. So let's go back to the original. We had 2x squared plus 1 over x plus 3, x minus 1, x minus 2. And then we had a over x plus 3. So a is equal to 19 over 20. So here's how you would plug it in. The 19 is in the numerator, and the 20 just goes into the denominator. So it would look like this, okay? Because essentially what you're doing, if we go back here, essentially what we're doing is we're doing a times 1 over x plus 3. So if a is 19 over 20, we multiply the numerator and we multiply the denominator. So 19 times 1 is 19. And then we have our 20 times x plus 3. Okay? So our denominator, when we have a fraction, our denominator of a is just going to go into the denominator of our rational expression here. And then that would be true for all of them. So that means that b was negative 3 over 4, so I'm actually going to write it this way now with a minus. It's negative, so we're just going to change this to a minus. The 3 goes in the numerator. The 4 goes in the denominator with the x minus 1. And then we have c is 9 over 5. So that's positive. The 9 goes in the numerator, and the 5 goes in the denominator with the x minus 2. And that would be our final answer here. Now, I want to start method 2, okay? Method 2 is far more algebra heavy, but I want you to just get an idea as to how it works. We're not going to use method 2. We're not going to finish it, okay? We're just going to get it to the point where we have the coefficients, the corresponding coefficients equal to each other, okay? Just so that you get accustomed to this. So let's put this in a different color. We're going to do method 2. Same problem. So we had 2x squared plus 1 is equal to a times x minus 1 times x minus 2 plus b times x plus 3 times x minus 2 plus c times x plus 3 times x minus 1. So this is a far more algebraic heavy, as I said. There's a lot more algebra here because our first step is to multiply all of this out, okay? So here it's not just distributing the a to one thing, it's taking the x minus 1 and x minus 2, multiplying it, and then distributing the a. Taking x plus 3 times x minus 2, multiplying it, and then distributing the b. X plus 3 times x minus 1, multiply, and then distribute the c. So it's extra work here because you're doing a lot more multiplication. So let's actually do that. So you get 2x squared plus 1. Do this in 2 steps. I would recommend it. So x minus 1 times x minus 2 gives us x squared minus 3x plus 2 times a. Then x plus 3 times x plus 2 times x minus 2 gives us x squared plus x minus 6. And then we have plus c, and we have x plus 3 times x minus 1, which gives us x squared plus 2x minus 3. Okay, so we multiplied all of our quadratics first, and then we're going to distribute our constants. So we have ax squared minus 3ax. So notice I put the 3 first. There's not any specific reason for that other than it looks nicer. Plus 2a. Then we distribute the b. So we have bx squared plus bx minus 6a. And then finally plus minus 6b, sorry. Plus cx squared plus 2cx minus 3c. So we distributed the constants here. So first we multiply. Multiply each of these factors together. And then we distributed the constants. Now we're going to rearrange. So like terms are together. So that means all of the x squares are together, all of the x's are together, and all of the constants are together. So it can look like this. The ax squared plus bx squared plus cx squared. Then we have negative 3ax. We have a plus bx. And we have a plus 2cx. And then we have our constants. So constants are 2a minus 6b minus 3c. And we're just going to group these together and factor. So we're going to factor out x squared. Then we're going to group these together and factor out x. These have no power of x, so these are just our constants. So what we have here is 2x squared plus 1 is equal to, we're going to put the x squared in back, a plus b plus c times x squared. Then we have plus negative 3a plus b plus 2c times x. And then the last part, we're just going to put it in parentheses so that we know it's together. Okay. Well, now we're going to equate our coefficients on the left with our coefficients on the right. So keep in mind that this 2x squared plus 1 is in standard form. This is 2x squared plus 0x plus 1. So that means that our coefficient of x squared on the left is 2, so that's going to be the coefficient of x squared on the right. The coefficient of x on the left is 0. There was no x, so the coefficient is 0. So that's going to be the coefficient of x on the right. The constant on the left is 1, so the constant on the right is 1. So we can set up a system of equations, and you'll see why we don't like it, where we say a plus b plus c is equal to 2, because that's the coefficient of x squared. Negative 3a plus b plus 2c is equal to 0. And 2a minus 6b minus 3c is equal to 1. And we have to solve this system. So we've never actually done a linear system of equations with 3 equations. Essentially what you would be doing is you can use elimination, okay? You would try and solve 2 at a time, where you figure out, okay, here's what b plus c is. You can use elimination, but I would probably recommend substitution, where you substitute in what a is. So a is 2 minus b minus c. You could plug that in here. And then from here, you can combine like terms and use elimination. Okay, substituting in into both of these. Or you can use substitution again. Okay, so it's a much more complicated thing. I don't want to spend a lot of time on solving a system of 3 equations. I just want you to see that you can do it. You can absolutely do it. It's just a lot more time consuming. Substitution is probably the easiest way. So we're not going to do that, but you absolutely can. So this is a case where it's so much easier to do it using the first method. Okay, let's take some examples where we have something quadratic. Okay, and we're not necessarily going to go through and do an extensive solution. We're going to try and keep it simple. And then we'll take a quick look at the process for improper fractions. But we're not going to do any improper fractions. So let's take one example. Sorry, I'm just looking at my sheet to... Let's do the example of, that was number 2, or number 3, that was number 3, so number 4. And in most of these, if it's linear, okay, with linear factors, I will ask you to solve for the constants. In some cases, I won't, okay? And if I say don't solve for the constants, essentially what we want is this. If we say do not solve for the constants, you would stop here. You wouldn't do any of this extra work. Okay? Okay, let's take a fourth one where we have quadratic factors, just so that you see how it works. So let's say that we have 3x squared plus 4x plus 4. And we're going to divide this by x cubed plus 4x. Okay, So we're going to solve this one all the way through. We're going to solve this using the second method, okay? And then for everything after that, we're not solving for constants, okay? So after this, it's going to go much, much faster. So first thing that we do is we factor. So we have 3x squared plus 4x plus 4. And if we factor, we wind up with x times x squared plus 4. So we were able to factor out an x. X is in common for both of these terms. And because we can factor out an x, we have x times x squared plus 4, but x squared plus 4 is not factorable. Okay? This is a sum of squares, it's not a difference, so we can't factor this any further. So we have two fractions, so I'll rewrite this here. 3x squared plus 4x plus 4 over x times x squared plus 4. And here we have two fractions because we have two factors here. First one gets an x, second one gets an x squared plus 4. Okay. This is linear. This x is linear, this first one. So it gets a constant. Now we said when it's quadratic, it gets, the numerator is in the form ax plus b. So we already used a, so we're going to write it as bx plus c. Okay, so this is quadratic. So the numerator is not a constant, it's linear. It's linear. Okay. Which kind of makes sense, right? In order for, so first of all, we need it to be less than x squared, right? We need these to all be proper fractions. They always have to be proper. So the degree of the numerator has to be less than the degree of the denominator. And we need to somehow wind up with an x cubed in the denominator. So we have to, this has to be, the degree has to be 1 less than the degree here. Right? So the only way that's going to happen is if we have an x here. Okay, if this were linear, there would be no way for us to wind up with an x squared up here. Okay, so we know that we multiply both sides. So I'm going to notice I put parentheses around the whole thing. So when I do that, I'm saying you're multiplying everything in the equation. So we've done that before. You've seen that before. This is going to cancel. And what we wind up with is 3x squared plus 4x plus 4 is equal to a times x squared plus 4 plus bx plus c times x. So we're going to do this using the second method, okay? If we plug in 0, by the way, we can eliminate the b and the c and solve for a, okay? And if we plug in 2, but there would be no way to eliminate the a and the b to just be left with c. So we can, in other words, we can solve for a by using the first method, but we can't solve for b and c by using the first method. So that's why we're just going to use the second method, okay? Hopefully that was clear. We can get rid of the b and the c so that we could solve for a, because we can just make x 0, and then we have 0 times bx plus c, and we're left with just a. But there's no way to get rid of, let's say, the a and the b so that we can just have c left over. That can't happen, okay? So that's why we're using the second method. So we're going to distribute. So we distribute the x, and we distribute the a, and fortunately we're not multiplying any quadratics, so this is an easy distribution. So now we have 3x squared plus 4x plus 4 is equal to ax squared plus 4a plus bx squared plus cx. Now we can rearrange, okay? We want to rearrange it So our exponents are going down, and so that we combine like terms. So the a and the b are going to be grouped together. So we have 3x squared plus 4x plus 4. We have an ax squared and a bx squared. Then we only have a cx and we only have a 4a. So the only thing that we have to do is we have to factor out the x squared from these first two terms, okay? Because we already have just a cx and just a 4a. There are no other x's, so we don't have to factor out an x anymore. So that's going to give us 3x squared plus 4x plus 4 is equal to a plus b times x squared plus cx plus 4a. So now we're ready to, we call it equating the coefficients. So a plus b is equal to 3. C had already solved for us. C is equal to 4. And 4a is equal to 4. So a plus b is equal to 3. The coefficient of x squared is the same on the left and the right. The coefficient of x is the same on the left and the right. So notice we already have c. The constant is the same on the left and the right. So we can use this. This isn't even a system. We can use this to solve. So if 4a equals 4, then a is equal to 1. So we have c, we have a, and now we need to solve for b. So a is equal to 1, so 1 plus b is equal to 3, so b is equal to 2. So this was a really, really fast solve, okay? So even though we used that second method, this was so fast, and it was faster than plugging in x equals 0, solving for a, and then having to do this anyway, okay? The only time that that could be helpful is like in the last problem where you had a really complicated system. Then it could be helpful to do something like that. So what we have here then is we could write out our final answer, 3x squared plus 4x plus 4 over x cubed plus 4x. And this is equal to a, which is 1, over x, plus, and then bx plus c. So b is 2, and c is 4, over x squared plus 4. Okay? And that's how you solve for the constants. So in the future ones, let's not solve for the constants, okay? So we're not solving for the constants anymore. We're just doing denominators. So we're just going to take a bunch of examples, and we're just going to go through how you go about doing it, and this is not super complicated, okay? We're just going to go through a bunch, just so that you get accustomed to working with the denominators, and then you could use all of these as examples of how to solve for the constants. So let's say, for example, we had 3x plus 8 over x minus 4, x plus 2, x squared plus 1. Okay, and then let's even add in, since we're not worrying about solving for the constants, x squared minus 3x plus 3. Okay, so first of all, x squared plus 1 and x squared minus 3x plus 3 are not factorables, so we don't have to worry about that. And if I'm telling you not to solve for the constants, you should still make sure that you don't have things that are factorable. So we have 4 fractions here because we have 4 factors. So we have 3x plus 8. So the first denominator is going to be x minus 4. Again, the order doesn't really matter because you're adding, but we may as well do it in the order it was given to us. X plus 2, then we have x squared plus 1, and we have x squared minus 3x plus 3. So you should be seeing if you could fill in the tops. Okay. X minus 4 is linear, so its numerator has to be constant. X plus 2 is linear. Numerator must be constant. X squared plus 1 is quadratic, so the numerator is linear. So we already used a and b, so we're going to use cx plus d. And x squared minus 3x plus 3, it's quadratic. Numerator is linear. We already used the other letters, so we're going to start at e. So it's ex plus f. And that's it. We're not going to go any further. And by the way, if when you solve, you get something with x cubed on the right, but it doesn't exist on the left, you would just say that that's equal to 0. So, for example, if there were no 3x squared here, but you have an x squared over here, you would have just said, okay, a plus b is equal to 0. Okay, so even though it doesn't exist, and even though it wouldn't be part of standard form, if it's on the right, then on the left, you just make it equal to 0. Okay. Okay. Let's take one other type of instance before we talk about improper fractions. The other type of instance is if you have something that's linear, but think of it as like a multiple, as a multiplicity greater. So if we have something, a factor that has multiplicity greater than 1, then it works a little bit differently. Okay. So let's take an example. Let's say that we have, I'm going to keep these numerators simple because it really doesn't matter. 6x squared minus 7x plus 2. Our numerators are irrelevant because we're not solving for constants right now. Let's say that we have an x plus 1 squared. Okay. Well, this is really, this is really a factor that has a multiplicity of 2. So we're going to have 2 fractions, but it works a little bit differently. One of them is going to have an x plus 1, and the other one is going to have an x plus 1 squared. Okay? Now this kind of makes sense. Think about it if you were to find a common denominator. If this were just x plus 1, okay, so we have x plus 1 and x plus 1. The problem with doing that, as having both of these as x plus 1, is that the common denominator would just be x plus 1. But this is an x plus 1 here. This is x plus 1 squared. So when we do this, we have to think of the denominators, okay? So we need a common denominator of x plus 1 squared. The only way to get that is if one of our denominators is x plus 1 squared. Okay, so you might say, okay, well, x plus 1 squared I could write as x plus 1 times x plus 1, but we need a common denominator of x plus 1 squared, and if we have x plus 1 and x plus 1 here too, then that won't happen. Our common denominator is just x plus 1. Okay, but both of these are considered linear, so we would have an a and a b, so this is not considered quadratic. You're only looking at what's inside the parentheses. So we need the common denominator. To be x plus 1 squared. why we divide it up this way. Okay. But then when we figure out the numerators, we're looking only at what's inside the parentheses. Inside the parentheses is something that's linear. That's why we have a B here. Let's take another example. Let's say that we have 2x plus 1 over x cubed times x squared plus 2 squared. Okay. So we're looking at the multiplicities with the degree, okay? That's what we're looking at. The degree here is 5. I don't really want to say that. That's not really the degree of the polynomial down here. We're looking at the multiplicities. So we have 3 and we have 2. That means that we're going to have 5 fractions. So I'll show you how that works. So we're adding them. You're always adding them until you find the constants. Okay. The x cubed, well, you could have an x. You could have an x squared, but you need an x cubed in order for the common denominator to be x cubed. So notice you keep going up until you reach this power. So you have denominators. Of each power of x until you reach 3. Again, it has to do with the fact that your common denominator would have an x cubed in it, okay? So we have x squared, x cubed, and then we're going to do the same thing with the x squared plus 2. You have an x squared plus 2 to the first and an x squared plus 2 to the second. So you start at 1 and you keep going up until you reach that power. And then you look inside the parentheses to see, is it linear or quadratic? So x is linear, so it's A. This, think of it as in parentheses, x squared. X is linear, so you have a B. X is linear, so you have a C. Okay? So the only way that you're ever going to have anything potentially quadratic is if you're adding or subtracting to your x to some power, okay? So this you're adding 2, so this is going to be a dx plus e, and this is going to be an fx plus g. So here, this is still linear. You're not adding or subtracting anything from x squared. Let's do one more example. Okay. Let's say that we have 3x cubed plus 7x squared minus 1. Numerator is kind of irrelevant. Let's say that we have an x to the 4th times x squared plus 6 times x squared plus x plus 1, and we'll cube that. So let's look at how many fractions we have. Well, here's an x to the 4th. We're going to have a fraction for every power of x, not x to the 0, because x to the 0 is just 1, so that wouldn't do anything. We're going to have a fraction for every power of x up to 4. So there are going to be 4 for this one. Here, notice there is no exponent, so there's only going to be 1 for the x squared plus 6. And here, this is a 3, so that tells us there are going to be 3 for this. Now, notice x squared plus x plus 1, not factorable, okay? And actually, I'm going to add in 1 extra here, just because I want you to see one extra thing. So let's add in a 2x plus 1 squared, just for the fun of it. Okay. So that means that we now have 4 plus 1 plus 3 plus 2 fractions. Okay, so that's going to be 10 fractions. So we're going to write this all out. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So let's just do the bottoms first. So we have the x to the 4th, which means that we're going to have an x to the 1st, an x to the 2nd, an x to the 3rd, and an x to the 4th. That takes care of the x to the 4th. Okay, in a different color, let's do the ones that are associated with x squared plus 6. So there's actually only one, because x squared plus 6 is just raised to the 1st power. Then we're going to do all of the ones associated with x squared plus x plus 1. Well, we have 3 of those, because we have x squared plus x plus 1 to the 1st, x squared plus x plus 1 to the 2nd, and x squared plus x plus 1 to the 3rd. Okay, and finally the last one, the 2x plus 1 squared. Well, we have a 2x plus 1 to the 1st, and then we have a 2x plus 1 squared. Okay, so now we just have our numerators. So numerators are nice and simple. It's either going to be in the form of a constant or it's going to be in the form dx plus e or ax plus b. So all of the x's are linear, right? Because the power is irrelevant here. We're ignoring the power on the outside. So x, x squared, x cubed, and x to the 4th all get just letters. A, B, C, and D. Now we look at this x squared plus 6. This x squared plus 6 is quadratic. So it's in the form ex plus f. We're just going in the order of the alphabet. It doesn't matter that much. You just don't want to repeat letters. Okay, so if you skip a letter, don't worry about it. Now we're going to look at these. So x squared plus x plus 1, that's quadratic. So this is going to be gx plus h, ix plus j, and kx plus l. Now we're going to look at the 2x plus 1. So 2x plus 1 is linear. So we have m here, and then here again, 2x plus 1 is linear. This square is on the outside. It's irrelevant. So we have m plus n. Okay, so one quick thing. We're not going to do any examples of these. I just want to tell you what to do. So for improper fractions, so the thing is that you can't do partial fraction decomposition on improper fractions. So what that means is if you remember, when you're dividing, okay, you have your dividend over your divisor. Now you can't do anything with this if it's a proper fraction, okay? Right? 3 over 4 you can't divide. Otherwise, your dividend over your divisor is going to equal your quotient plus your remainder over your divisor. So if you have an improper fraction, you're going to divide, and then you're going to do a partial fraction decomposition on this. So you have to do your log division first. Then everything is the same. It's just that the fraction that you're using to do that partial fraction decomposition is the remainder over the divisor. Because that has to be proper. Okay? If you remember, we say we know we're done when the degree of the divisor is greater than the degree of the remainder. That's how we know when we're done with division. Okay, so we do long division first. It's usually going to be long division. Okay, you would do your long division first, and then you take your remainder over your divisor, and you do partial fraction decomposition on that. Okay, and that's it for partial fraction decomposition. The next thing that we're going to look at is rational functions. So we've been looking at rational expressions. We're going to be looking at rational functions and what they look like on a graph, and then that'll be it.